Okay, thank you very much for the introduction, and oh, wow, this is loud. And big thanks to the organizers. It's a pleasure and a privilege to be here. Now, it's a little weird. I'm going to talk about new results and renormalization of critical circle maps, and sort of half the talks in the last few days were on critical circle maps, so I'm not sure how much or if I should even say anything. You know, there's this old Russian joke from the Soviet days. And a guy stands in the middle of the Red Square in Moscow and handing out pamphlets. And back then it was, you know, a serious political insurrection, so the police come immediately to arrest him. A policeman grabs the pamphlets from his hand, looks at them, leaves through, they're all blank, just blank sheets of paper. So policeman asks the guy, why is there no writing on them? He says, comrade, there's no need to write anything, everything is clear. Right, so anyway, so even though everything is clear, at the risk of boring you in, let me very quickly review some of the known results on renormalization of critical circle maps. And I'll only talk about analytic critical circle maps. So somehow, well, if you, first of all, if you already saw some review of the results of in the smooth case, the state-of-the-art theorem, I guess at the moment, is the result of Welington, Pablo Guarino, and Marco Martins, which got mentioned a few times already in this conference. But let me stick to the analytic case, and somehow historically in this subject, the results were first proved in the analytic category and then extended to the smooth case. So let's start with what everybody knows. We look at critical circle maps. So the circle is R mod Z, a critical circle map F maps the circle to itself. It's a homeomorphism, as I said, analytic, single critical point, which we can put at 0 just to fix the ideas, which is of cubic type. Now, just for the moment, let's say that the rotation number is irrational. And then we have a sequence of renormalization of this map. And renormalizations are, as always, rescaled first return maps. It doesn't really make very much difference where, on what part of the circle you consider first return maps, as long as you are consistent. Historically, the choice that's made is the following. You have a dynamically marked orbit. That's the orbit of your single critical point, 0. You look at a special sequence of first returns, which are given by the continued fraction convergence of the rotation number. So this is 1 over A0 plus 1 over A1 plus etc. Then this is a finite continued fraction. And you take the interval between the two returns of this type. Maybe it's worth noting that these are not the only closest returns of 0, but these definitely are closest returns of 0. That is between 0 and this iterate, there is no smaller iterate of 0. So when we look at the first return map of this interval, it's an elementary exercise, just because these are closest returns, to see that it's given piecewise Is blue visible on this board? Good. Well, it's okay, but it's visible, right? It's actually blue. So this is blue, and is pink visible? Can you see that the pink is different from the blue? Good. Okay, so on the pink interval, it's the iterate fqn plus 1, which shifts it over like this. I mean, these are all homeomorphisms, right? We're basically talking interval exchange maps, except they're nonlinear. And on the blue, it's the iterate fqn, which shifts it over like so. And of course, this point is the same. It's fqn plus qn plus 1. And you all know the story, but still it's worthwhile to repeat this because it has motivated much of the work that followed. You want to rescale this, and there's a bit of a problem with rescaling this back to a circle map. It's not very hard to get a circle map out of this. You could use your blue map as a local chart to glue together the ends of this interval, right? Say the neighborhood of this point to a neighborhood of this point. And then this pair of maps, this first return map, gives you a well-defined analytic map on the quotient manifold. And the quotient manifold is, of course, a circle. I mean, just the interval with two ends glued together. But the problem is that this circle is not an affine circle. The glue-in has the same smoothness as F, so in our case it's analytic. There is no canonical affine structure on this new circle. And therefore, you haven't recovered the circle map out of this. You haven't rescaled this back to a circle map. What you've recovered instead is a conjugacy class of circle maps. Any analytic circle map in this conjugacy class would do. And that's not a good thing. So well, it's just not good. Because some things are good, and this is not good. And so, well, I mean, you started with a circle map. It would be good to get a circle map back, but you don't, so it's not good. But as I guess Marco would put it, the solution is just don't glue. And so you don't glue, and this is what people did classically, i.e. from late 1980s, 1970s, I'm sorry, early 1980s, before I was born. Wow. Not quite, but anyway. So switching to considering pairs of interval maps rather than maps of the circle. If you just think of this as a pair of interval maps, well, you need one additional. So you just, well, I mean, you reproduce this picture. Here's a 0. There's a blue map. Oh, my blue was below, so it goes like this. And there's a pink map. And that goes like that. And you give them names, say eta and xi, and the whole thing zeta. And these are analytic maps. They're analytic on slightly larger intervals. And the condition that you want to put here to make sense of the dynamics and of this glue-in construction is a commutation condition, right? You want xi composed with eta to be eta composed with xi, really just in the neighborhood of 0, because that's the only place where the domains of definition would overlap. And this is called a commuting pair. And then if you think of this as a commuting pair, then you don't need to glue to normalize this. You just rescale linearly. And traditionally, you rescale it linearly in such a way that this bigger interval becomes 0, 1. And then the smaller one falls where it may. And that's the definition. Now, let me summarize the renormalization hyperbolicity statement in this case by a picture. And this picture in this generality is due to Oscar Lanford, and it was known as the Lanford's program. And the picture looks like this. So these pairs have rotation numbers, right? They correspond to conjugacy classes of critical circle maps. Renormalization acts as the Gauss map on the rotation numbers. So renormalization has the rotation number fractional part of 1 over the rotation number of the original pair. And then you have the following picture. So let's say this board is the space of analytic commuting pairs. And don't worry about the manifold structure on that for the moment. Let's just say we found it somewhere. We partition this space, so I would like to imagine this space as a cylinder where this direction, the circle direction, is responsible for the rotation number. So just think of, model maps composed with the rotation. There are vertical strips in this cylinder, call them Sn, which consists of pairs whose rotation number is a continued fraction starting with n. Okay? There's also S infinity. These are the ones for which the rotation number is 0, and you cannot renormalize even once. And then you have this picture. It's S1, S2, S3, etc. There are infinitely many of them. Here is S infinity. Sns accumulate here. And your renormalization forgets the first digit of the continued fraction. So in the circle direction and the horizontal direction, it maps each of these strips around the whole cylinder. Right? And then hyperbolicity means that in this context that it contracts uniformly in the vertical direction. So S1 gives you this. And S2 gives you that. The image is actually disjoint. And so on. So we have a horseshoe. And there's a horseshoe attractor. It's hyperbolic, etc., etc. So this is a theorem. I mean, the way I formulated the hyperbolicity statement, it's a theorem of mine. There's a lot of work that various people did in proving this picture. Again, as you know, and as got mentioned a few times, in particular, Edson and his thesis proved the existence of part of the horseshoe attractor, namely an attractor for bounded type pairs. I mean, bounded type just means that you take finitely many strips rather than all of them. Then Edson and Welington proved that convergence in that case to that part of the horseshoe is geometric. And then I constructed the rest of the attractor and proved the hyperbolicity. And let me just point out that there is an issue with proven hyperbolicity here, which has to do with the setup. See, the space of analytic commuting pairs is really not a Banach manifold. And that's, Charles, that's perhaps why this is bad, right? I mean, you're talking about a space of pairs of analytic maps, which is, of course, a Banach manifold, but with a commutation condition, which is some crazy infinite codimension condition. And it's hard to put some sort of a sensible structure on this space directly. Okay? So to circumvent this, one can do a different sort of gluing. And this already got mentioned in Misha's talk in relation with Siegel disks, which is called cylinder renormalization. And cylinder renormalization, well, let me do it in this picture. Okay, so in cylinder renormalization, let's make a little bit of an extra assumption. let's assume that, say, my blue iterate with which I'm gluing, I mean, these are analytic maps, so they extend beyond the circle. Let's imagine that this guy has a repellent fixed point here, outside of the circle. And then there's a symmetric one below. And let's also assume that you can connect these with the curve. In such a way that, well, I guess this is my curve. This is an ugly picture, I'm sorry. But anyway, this is a curve whose pullback by the iterate FQN is disjoint from it except at the endpoints. You could tweak it then at the endpoints to make sure that the quotient of this domain, of this fundamental domain by FQN is a cylinder. So let's call this domain something C. C mod FQN of Z is a cylinder. You could make it a bi-infinite cylinder, C mod Z. And then the magic is that C mod Z does not have any non-affine analytic isomorphisms, and therefore there is a canonical affine structure here. So this highly nonlinear change of coordinate restores the affine structure on this interval. And you get back a circle map. So you start with the circle map, you do this non-trivial rescaling, and you get back a circle map. And now you are inside a Banach manifold, and that's where this picture lives. Okay? So let me refer to this picture as a renormalization hyperbolicity statement, hyperbolicity theorem, just so I don't have to reformulate this in different contexts. And another thing that I would like to formulate is a corresponding rigidity statement. And the rigidity theorem is that if rho of f is equal to rho of g and is irrational, and you take a conjugacy between the two, which fixes 0, then H is quite smooth. Then H is C1 plus alpha smooth at 0. And then you also have extra smoothness dependent on the rest of the circle, dependent on the rotation number. So for bounded type, for instance, it's C1 plus alpha smooth on the circle for bounded type, and it's C1 smooth in general. So the first two statements for bounded type, well, I mean, this statement for bounded type was proved by Edson and Welington. The C1 plus alpha conjugacy in general was done by Khmelov and I. And C1 is Kostya, Hanin, and Teplinsky. And you know, C1 plus alpha smoothness at the critical point is stronger than exponential convergence of free normalization. But in fact, the way the proofs work, it can be derived from exponential convergence of free normalization. It's not much stronger. So all right. So in a sense, it's a corollary. Well, not in a sense, but directly it's a corollary of this picture. So let me call this a renormalization hyperbolicity theorem, and this is a rigidity theorem. So when I talk about different classes of maps, I don't have to reformulate the theorems. Okay, good. So now let me tell you about the motivation for this talk. The motivation for this talk was Edson. He actually gave a version of his talk here in Sebastian's conference in London, and he mentioned there that renormalization theory is really only developed for the cubic exponent, and which got me motivated to give this talk. So so let me tell you other scenarios in which these two statements can be proven in the analytic case. Okay, so again, I only stick to the analytic case. Okay, so let's start with something that. Mm-hmm. Okay. 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 Super. So, I'm not going to. I'm not going to. I'm not going to claim very much credit, but let's just summarize. So, all right. So let's start with the case of analytic maps with arbitrary odd exponents, right? So, critical point of order n, which is 2m plus 1. M is a natural number. Okay, and no, listen. I hear your thoughts loud and clear. Everybody knows that this is true, and the theory goes through. I mean, the complete theory with the hyperbolicity and rigidity just the same as in the cubic case, which is almost the case. So there is one small wrinkle. And right, and that small wrinkle is the following. So there is one, and Edson, I mean, I would imagine that probably was also in your student's thesis, although I'm not familiar with the thesis. But let me just say what needs to be proven to push the whole theory through to an arbitrary odd exponent. It's not that much. What you need are rigid families of model maps. You need model critical circle maps which have a rigidity property. They should not admit any non-trivial quasi-conformal deformations. Okay? So, need a family of, so let's say a rigid model family of critical circle maps. So, model just means that you get all of the rotation numbers and all irrational rotation numbers exactly once. And rigid here means no non-trivial quasi-conformal deformations supported on the closure of the preimage of the circle. So if you take the union of f minus n of t, close, an invariant Beltrami that lives here cannot produce any quasi-conformal deformations. So, okay, and this is a very amusing exercise that I'm going to do right now. At least I found it amusing. It's sort of an Olympiad type problem. So here is a little lemma, which I hope you'll like. So again, n is equal to 2m plus 1. M is a natural number. So there exists a unique Blaschke fraction, call it Bn, such that Bn is a homeomorphism of the circle. 1 is a fixed point of order n, of multiplicity n, sorry. Multiplicity n. 0 and infinity are fixed points of multiplicity m plus 1. And of course, by Riemann-Hurwitz, that means, oh yeah, degree n. So by Riemann-Hurwitz, this means no other critical points. Okay? Fixed point. It's fixed. So this is super attractant. But of course, if this is true, then you get the whole model family just by multiplying this by rotation, right? These are fixed and critical, right? So multiple critical point. Right. So then the model family is just this times rotation. So here is a proof which, like I said, again, I don't claim very much here. It's an exercise. Maybe you guys have seen it. I didn't. So, and I kind of liked it. And it's short. And I got to give you at least one proof. So here, proof. Take the binomial expansion of z minus 1 to the n. Okay, it has n plus 1 terms. So 2m plus 2 terms. Let's split them. Let's separate the first m plus 1 from the second m plus 1. So the higher powers of z would be the sum. K goes from 0 to m, and choose k, z to the k. And n minus k, I said higher powers, right? What? I'm sorry? Z minus 1 to the n. Yeah, sorry. Minus 1 to the k. And then, so I call this p of z. And then let's just take the tail of this and call this minus q of z. Okay? So I claim that Bn is p over q. It's a trivial exercise to see that q of 1 is not 0. Easy induction. And that immediately proves that it has all the right properties except the fact that it's a Blaschke fraction. Okay? Right? I mean, obviously. So to see that it's a Blaschke fraction, notice that q of z is z to the n p of 1 over z. Okay? So if this guy has a real root c, then the numerator would have a term z minus c, and the denominator would have the term 1 over z minus c, and you can throw in a z from here. Okay? And if it has a pair of complex conjugate roots, alpha, alpha bar, then you do the same exercise with both of them. Okay, that's the proof. I mean, you pair them like that. So, which is nice. So, right. So this is the only missing piece. So that is enough to extend both of these statements to the case of an arbitrary odd n. again, not saying that this is some sort of huge scientific breakthrough, but cute. Okay, so let's now talk more serious things. By the way, something I forgot to mention in the beginning, and now it will be a little out of context, but I should mention it at some point. So there is an alternative approach, alternative to cylinder renormalization, to prove in renormalization hyperbolicity, which is renormalization of almost commutant pairs, which was done by Denis Gaidashev and I. It's a harder path to prove in renormalization hyperbolicity, but it's a path that generalizes to higher dimensions. And we used it to prove, in particular, a conjecture of Enrique Pujals on critical circles in families of real analytic maps of the annulus. But I've given a bunch of talks about that recently, and so I don't want to give another talk on that. And if you haven't heard those talks and you're curious, you can ask me later. All right, so let's talk some harder stuff. So this takes care of all critical circle maps, which are actually analytic on the circle. But as Edson mentioned in his talk, you could have other types of singularities. I'm still, for the moment, sticking to a single critical point. And the type of singularities will now be an arbitrary alpha. Okay? So we're talking about maps which at 0, which are analytic everywhere but 0. So F is still a homeomorphism. Analytic except at 0. And at 0, the order of the critical point is x times absolute value of x alpha minus 1, where alpha is greater than 1. Okay. So, theorem, and this is a joint work, recent joint work with Igor Garbovitsky, who's also present here. Any. Right. But I'm not going to formulate the theorem for any. What I'm going to say is that there exists epsilon such that if alpha minus 2z plus 1 is less than epsilon, then we have renormalization hyperbolicity and rigidity. Okay, so for the moment we only wrote this for bounded type, and believe me, it's already a lot. A lot of work to write this for bounded type. I certainly, in general, there is probably no philosophical difference between bounded type and unbounded type, but there is a big technical difficulty because you have to understand the limiting case, which is a parabolic case, and that's an extra layer of complexity. For the moment, I'm only stating the result for bounded type. Now, let me be careful, okay? So let me say for any n equal to 2m plus 1, there exists epsilon such that this is, I mean, we can probably claim it uniformly for all, but let me just not push it. Right, so a couple of comments. I can't tell you the whole proof. I mean, it's not like this proposition. But on the bright side, there is a preprint on the archive, which is about 60 pages long. So good bedtime reading. But a couple of things. First of all, the theorem is local in alpha, but it's global with the rigidity statement. Okay, the rigidity statement is global. This is true for all. So if you fix alpha, this is true for all maps of this type. Okay, so renormalizations converge uniformly. And there's a, right, so as a side remark, which was motivated by Marco's talk, let me also say that our approach also works for unimodal maps of the interval. And we are, so this is already written. That is something that we are writing right now, but the statement is the same, except here the ends will be even. Okay? Now, just a little bit of the flavor of why this business is actually doable. And the thing is, if you try to think, I mean, let me first try to convince you that this is hard in some way. Because if you try to think of these maps in terms of commuting pairs, in a way you don't even know where to start. So you have a pair of maps, both of which have an essential singularity here at 0. So somehow the next sentence is completely unclear. Okay? But the magic is that cylinder renormalization doesn't care about that at all. Right? So if you think of this picture that I had before, then to actually define this change of coordinates, which carries out my renormalization here of my map, all I need is to uniformize this Riemann surface. That is, I don't need to know anything about the map inside this fundamental domain. I only need the analytic continuation of the map along this curve, which is quite far from the singularity, at least, you know, locally. So it's not that simple. I mean, it doesn't quite, I mean, it's true that cylinder renormalization can be well defined, but you still have to say in what class of maps you work. The class of maps that we work here is not really a class of maps, but a class of triples, if you like. There are two analytic homeomorphisms, and then there is a number alpha, and you should think of this as psi of phi to the alpha. Right? But really, that's, I mean, really it's the triple that you want to work with and prove the statements for phi and psi. Okay? So now, the renormalization that we work with is actually defined globally for all alphas. And if you take that statement for granted, then the theorem is nearly obvious. I mean, somehow the correct definition of renormalization defined in the Banach manifold structure and so on is as is almost all the work. Because if you can do it consistently for all alphas, then you get a hyperbolicity result for alphas which are small perturbations of odd numbers just by continuity. And if you think about it, you get a rigidity result just by continuity as well, because this is equivalent to exponential convergence to the horseshoe. Okay? Your horseshoe is a compact set. So your hyperbolicity picture survives in the neighborhood of this compact set for small epsilons. Okay? So in a sense, so far, most of our work went in the direction of appropriately defining renormalization, and as I said, that's a fairly long story. And of course, there is eventual hope of proving this for all alphas, but I'm far from claiming that we know how to do this at the moment. Okay, but at least this is a framework which exists for all alphas. Okay, and I guess I have time to make one more bold claim. So let's do one more theorem. So the previous two are written. This one is not, but will be written soon. And it's the obvious question: what happens if you have many critical points? Okay? So just as a proof of concept, bicubic. So there's an obvious parallel with Daniel Smania's talk, who talk about bimodal interval maps. Here we're talking about homeomorphisms, analytic homeomorphisms of the circle with two cubic critical points. And I'll explain why they have to be cubic in a moment. Okay? Of course, renormalization hyperbolicity here is somewhat different from this picture, because now there are two unstable parameters. One of them is still the rotation number, and the other should be thought of as a distance between the two critical points, but it's not the distance, it's a relative distance. Well, I mean, it's a sign of maturity of working on this subject if you say that the other parameter is the invariant measure of the arc between the two critical points. So this is C1, C2, and you take the invariant measure lambda of this arc. But what you really mean to say is that this is a critical circle map with an irrational rotation number. You take the topological conjugacy to the irrational rotation. This is a terrible notation I'm going to make. This rotation by rho. This point lands somewhere, this point lands somewhere, and you just measure the distance of this arc. Right? So that's your second unstable direction. I'm only, again, for the moment, only for bounded type. And again, not because I think this is fundamentally different, but because there's a different layer of complexity with right-hand stuff for unbounded type. Now, why bicubic and not, let's say, degree 3, degree 5? The reason is that the theorem about the existence of a rigid family of model maps for bicubic is in the literature. So, rigid family of Blaschke models is a theorem. And it's a theorem, it's an older theorem. It's a theorem by Said Zakari. It was in his PhD thesis, which I know exactly when that was. That was 1993. That was 1 year after my PhD thesis, 12 years after I was born. So he constructed this family as, well, he constructed a larger family of Blaschke models for cubic polynomials. And this is a highly non-trivial construction. Okay, this is not like the game that I showed you with the letter n. Okay? Other than that, at least for two critical points, there should be no difference again whatsoever for the theory. So take this as a proof of concept rather than a final result. I don't know, 2 minutes. I'm not going to throw any more theorems at you in the remaining 2 minutes. Welington, happy birthday. And you contributed very much to all parts of the subject, everything that I was talking about. There's a theorem of yours. People were saying how long they've known you. Well, I've known you since one of us was a grad student. So happy birthday. Thank you very much.